Okay, so till now we have seen all the elements, all the passive elements, three passive elements: resistor, inductor and capacitor. Now we will look at the sources. So the next topic would be the sources. We will classify the sources into two types: independent source and dependent source. Independent sources are further classified into voltage sources and current sources, and these are further classified into ideal. Let me consider ideal first. Ideal, practical. Similarly, current sources are also ideal, practical. Now, dependent sources are basically of four types. They are voltage controlled voltage source, voltage controlled current source, current controlled voltage source, and current controlled current source. Now, we have to go through all these sources one by one. I'll start with the independent source first, and in that I'll consider the ideal voltage source first. So let me consider ideal voltage source. Now, an ideal voltage source is symbolically shown like this. It has a voltage value Vs. It provides a current I. Now, for the current to flow, there must be a closed path. So therefore, I'll apply a load over here. I'll consider a load which is variable. So I consider a variable load, and this is my load voltage V, and I have load current I, and since they are in series, so this load current I is equals to the source current capital I. Now if I plot the VI characteristics, if I plot the characteristics of voltage versus current, I'll observe that this is my voltage, load voltage V and load current I. I'm plotting a graph between load voltage V and load current I. So I'll get a straight line. So here this voltage will remain Vs for all time, because the voltage source will supply a voltage of Vs and that will be dropped across load. And this voltage will not vary with current. Even if you change the current by changing the load, if I change the value of load, the current will change. But because of that, this voltage will not change. So load voltage will remain same. So I can write this as V is equals to Vs for all I. Now, from the VI characteristics, we observe that the voltage source is non-linear, because the VI characteristics is non-linear. So now an independent voltage source can be defined as an ideal voltage source provides a constant voltage to a variable load independent of the current drawn. So this is about ideal voltage source. Then we will go for practical source. Practical voltage source. Now, a practical voltage source will have a resistance in series with ideal voltage source. I'll have a resistor, internal resistance Rs. I'll call this as source resistance, and it will provide a voltage of Vs. Now again, for the current to flow, I must apply a load. So I'll apply a variable load over here. This is my load voltage V. This is my current I, load current I. Now I'm applying KVL for the first time in the subject. I'll cover this topic KVL later, but for the time being, just let me assume that I'm applying KVL. So just consider it directly. You will understand how did I apply a little later. So KVL implies, KVL I am applying in this loop. So it's Vs. So there is a current I which is flowing in this, and this I is equals to capital I. So V and current always enter into a resistance from positive terminal. So if I apply the KVL in this loop, I'll get Vs minus I times Rs minus V is equals to 0. Now if I consider load voltage, so load voltage will be Vs minus I times Rs, or it can be written as Vs minus I times Rs. So what we observe here that the load voltage varies with load current. So in practical voltage source, load current, load voltage, it's not load current, load voltage that is V varies with load current which is nothing but I. So V is a function of I. Now if I plot this in a graph, so what I observe that I'll get, first let me consider the previous one. This is for ideal source. Now for practical source, this will be decreasing line. So this is my current I, load current. This is my load voltage V. This is voltage Vs. Now the equation of this line is V is equals to Vs minus I times Rs. And at this point V is equals to 0. So what we have observed is the load voltage. The load voltage in a practical voltage source varies with the load current. Now let me give you an observation. If you make I equals to 0, that is when I is equals to 0, then V, that is load voltage V, is equals to Vs whenever current is 0. And when will current be 0? Current is 0 when it is open circuited. So therefore I can represent this diagrammatically like this. So therefore it is open circuited. I have load voltage V here. There is no current flowing through this, so there will not be any voltage drop across this Rs, and this can be equivalently drawn like this. This is V, this is Vs, this is Rs. There is no current flowing through this, so there will not be any voltage drop of this. So what we can conclude is, when the current through any passive element is 0, then the two end voltages are equal. For example, here when the current is 0 across Rs, the end voltages are Vs and V, they will be equal. This is a very important observation and it is used extensively in the problems. So we have covered ideal voltage source and practical voltage source. Next we will go for ideal current source. Now diagrammatically it is shown like this. So we have load voltage V. I am considering a current Is, and let me consider the load current as I. Now an ideal current source, sorry. So now if I plot the VI characteristics, now in this case I will plot I, that is load current versus load voltage. So what I will observe is it provides a constant current whose value is Is for all values of V. So therefore the current remains same irrespective of the load voltage V. So we can say that in an ideal voltage source, in an ideal current source, the load current is independent of the load voltage, load voltage. So the load current does not depend on load voltage here. Next we will consider practical current source. Again, like voltage source, it will have an internal impedance, but here the internal impedance will be in parallel. So this is my ideal current source. So to make it practical, I'll connect a current resistor in parallel to the current source. So this is IS, RS is the source resistance, and again I have to connect a load for the current to flow. This is my variable load, and I'll pass a current I across this. I'll assume a current I. This is my load voltage V. Now I apply KCL at this node. If I apply KCL at this node, so KCL implies minus IS plus, there will be a voltage V, because in parallel the voltage remains same. So therefore this voltage and this voltage are same. So the current through this branch will be voltage by resistance, that is V by RS. So this will be V by RS plus I equals to 0. So if I find the load current from this equation, I get IS minus V by RS. If I plot the graph of voltage versus current, I'll get, if I plot IV characteristics, this is my I, this is my V. So for ideal current source, we have already observed that the current is constant for ideal. But for practical, we will have a curve like this. Now here the current will be IS minus V by RS. This is my IS, and at this point current I is equals to 0. So what we observe here that in a practical current source, the load current varies with load voltage. Now again we will make one more observation over here. So let me consider one more observation. When V is equals to 0, that is the load voltage is 0, in that case I'll get the load current is equals to the source current. Now when V is 0, when the load is short circuited. So let me draw the diagram again. So here there is no load, we have short circuited the terminals, load terminals, and across short circuit we have V is equals to 0. This is my RS. So in parallel the voltage is same, so you will have 0 volts here also. So therefore a current of 0 ampere flows through this. This is my IS and this is I. So what we observe is this current I is equals to IS, because there is no current across across RS. This diagram can be equivalently drawn like this. So what we can conclude is current always chooses a minimum resistance path. Since there is no resistance in this path, so the whole amount of current flows through the short circuit. So what we can say that current always chooses low resistance path. Current always chooses low resistance path. This is very important. This is also used extensively in the problems, and this analysis is very important. Now, so we have covered all the independent sources. Next we will observe the dependent sources. So there is not, so a dependent source has a control variable. So let me draw the current control all the dependent sources. So as I have told you earlier that there are four types of dependent sources. Two of them are voltage sources and two of them are current sources. Now this is some K1 into V1 dash. This is some K2 into V2 dash. This is some K3 into I1 dash. This is some K4 into I2 dash. This source is nothing but, now this, the value of this source depends on a voltage and it is a voltage source. So a voltage is controlling this source, therefore it is called as voltage controlled voltage source. This is called as, this is again, let me correct this. Actually I should have considered a current over here. So let me consider some current I1 dash here and let me make correction here also. This is V2 dash. Now the value of this voltage source depends upon a current. So therefore this is a current is controlling this. So therefore it is a current controlled voltage source. This is a current controlled current source, whereas this is a voltage controlled current source. So we observe that in dependent source we have a control variable which controls its value. For example, in the first case, in the voltage controlled voltage source, this V1 dash is a voltage in some other part of the network and it is controlling the value of this voltage source, and therefore it is called as voltage controlled voltage source. Now there are a few very important points about the dependent sources. First is with respect to this control variable. The first point is with respect to the controlled variables only. The dependent sources are linear. They are linear. Make sure, just this is important. Dependent sources are linear, whereas independent sources are non-linear. Linear, they are active and bilateral. This is very important, that the control sources that are dependent sources, they are linear, active and bilateral with respect to the control variables. Then the second very important point is the control sources, they are not actually sources unless and until there is an independent source in the network. So the controlled sources or dependent sources, controlled sources are said to be sources that is an active element only in the presence of at least one independent source in the network. Now, why the presence of a independent source is important? Because when independent source is present, then only the control variable value, the value of control variable will be non-zero and the value of control source will be non-zero. So let me write that. Then only the value of controlled variable is non-zero and hence their magnitudes are non-zero. So this is very important point in terms of control sources or dependent sources. Please make a note of this. So with this we finish the dependent sources. There is not much about dependent sources. The theory of dependent source is very simple, but when it comes to the application, students generally face a few problems. So we'll help the students with the help of one or two problems. So now we are done with the dependent and independent sources. So we have covered two basics, that is the elements, resistor, inductor and capacitor, and then we have covered the sources. Next we will go for the Kirchhoff laws. The first Kirchhoff law is KCL, Kirchhoff's current law. Now KCL is defined at a node. It is defined at a node. Node can be a simple node or it can be a principal node. Now what is simple node and what is principal node? So simple node is an interconnection of only two branches, whereas the principal node is an interconnection of at least three branches. So it can be more than three branches also. So we have defined a simple node and a principal node here. So simple node has only two branches, whereas a principal node will have more than two branches. It must be minimum three. Now let me write the definition of KCL. So according to KCL, now different students study the definitions differently, but we will follow a standard definition that in a lumped electric circuit, for any of its nodes and at any time t, the algebraic sum of branch currents leaving the node is 0. Now in this there are two important words. One is lumped and this current leaving the node. These two are important. Now what is lumped electric circuit? So all the circuits which you will study in the network theory are lumped. The reverse of lumped is distributive. Distributive circuits, the distributive elements are found in transmission lines. That is, you cannot define their value. You cannot say that the resistance of a transmission line is 10 ohms, whereas you can say the value of resistor is 10 ohms. So that is the difference between a lumped and a distributive element. And now I have considered the current leaving the node. This is very important. Current leaving the node is 0. This is a standard definition which I will follow throughout the subject, and this helps a lot. This makes the subject very easy. You need not worry about incoming and outgoing. You need not worry about the directions. Just always consider the leaving currents. Do not go for the current incoming and outgoing. We will always consider the leaving nodes. Let me explain this with the help of an example. So let us consider a node on which there are 5 branches. So these are the 5 branches. Let me current consider across all of them: I1, I2, then I3, I4 and I5. Now at this node there are 5 branches. So the current in branch 1 is I1, which is going towards the node. Now according to KCL, so by KCL, what I am saying is sum of all the leaving currents is equals to 0. So leaving currents is equals to 0. Now what are the leaving currents? So in branch 1 the leaving current is minus I1, because I1 is incoming, so the leaving current will be minus I1. Similarly in branch 2 the leaving current will be minus I2. In branch 3 it is plus I3 plus I4 plus I5, and their sum will be equals to 0. That's what KCL says. Now from this you can take the terms on the right, and you can say that I1 plus I2 is equals to I3 plus I4 plus I5. So what you can say that this I1 and I2 are entering currents, and I3, I4 and I5 are leaving currents. So this definition is 100% correct. That is, sum of leaving currents is equals to 0. From this you can derive that the sum of entering currents is equals to sum of leaving currents. So generally students study this definition. This is also correct, but what I have said is this makes the subject very easy. I'll show you in the next topic in nodal analysis that this helps a lot. Now you know that I is equals to dq by dt. You know that I is equals to dq by dt. So if I substitute I is equals to dq by dt in the above equation, I'll get dq1 by dt plus dq2 by dt is equals to dq3 by dt, because we are at the same time, so therefore time will not change, dq4 by dt plus dq5 by dt. And from this I can write q1 plus q2 is equals to q1 plus q2 is equals to q3 plus q4 plus q5. And what is this? This is nothing but conservation of charge. Conservation of charge. So what we can conclude is KCL expresses conservation of charge. This is the first law of Kirchhoff, that is Kirchhoff's current law. Then we will see the Kirchhoff's voltage law. So next, the second law is KVL. Now, as KCL is defined at a node, KVL, it is defined in a loop or mesh, that is in a closed path. So to apply KVL, closed path is must. So let me write the definition of this. So according to KCL, again, in a lumped electric circuit, in a lumped electric circuit, for any time t in any of its loops, the algebraic sum of branch voltages around the loop is 0. Okay. Now, so let us understand this with the help of a diagram. So let me consider a diagram in which I have three elements, that is inductor, a resistor, an inductor and a capacitor. So how many branches are there in this circuit? There are three branches, because between every two elements there is a node. So there are three branches. This is one branch, this inductor is second branch, and the capacitor is third branch. So there are three branches in this network. Now if I consider a voltage V here, so this is my resistor, inductor and capacitor. I'll consider the drop across resistor as VR, since the source is present in the circuit. So therefore the current will enter from positive terminal of all inductor, resistor and capacitor. So let me consider the drop across inductor as VL and the drop across capacitor as VC. Now by KVL, I'll always consider the KVL, the drops in terms of potential. Now whenever I am going from negative to positive, whenever I am moving from negative to positive, I am gaining some potential, and whenever I am gaining, I'll consider that as positive. Whereas whenever I am moving from positive to negative, I am losing some potential, and therefore I'll consider that as negative. So hence KVL can be written as V minus VR minus VL minus VC is equals to 0. Because when we consider the source, I am moving from negative to positive, so I am gaining a potential. In resistor, inductor and capacitor, I am going from positive to negative, and hence I am considering them as negative. So now V is equals to VR plus VL plus VC. This is by KVL. Also, we know that ZR is equals to R ohms, ZL is equals to J omega L ohms, and ZC is equals to 1 by j omega c ohms. This will be useful later, but for the for the purpose of knowing, I'm telling you right now here itself. We'll cover this again in AC. So by KVL we have observed that the sum of all the branch currents is 0. Now since all the elements are connected in series, so the current through all of them will be same. Now we know that since V is equals to W by Q, we have already seen this, that is potential is energy by charge, and since we are in series, so the current remains same. So I is equals to dq by dt. This remains same in series, remains same in series, remains same in series. So now if I substitute this in the equation, in the previous equation, what I'll get is, I'll get W by Q is equals to WR by Q plus WL by Q plus WC by Q. Since all the elements are in series, I have not changed the charge, because since in series current is same and hence the charges are same. From the above equation I can write W is equals to WR plus WL plus WC, and what does this implies? This is nothing but conservation of energy. So what we can conclude is that KVL expresses conservation of energy. Now we have two important techniques. They are called nodal and mesh analysis. So nodal and mesh analysis. Now actually nodal and mesh analysis are nothing new, because nodal is nothing but it is the combination of KCL plus Ohm's law. That means when you are applying nodal, it means you are applying KCL and Ohm's law. Combination of KCL and Ohm's law is nothing but nodal. Then we have mesh analysis. So mesh is nothing but KVL plus Ohm's law. We'll understand them with the help of problems directly a little later. I'll solve all the problems at the end of this chapter. Once I complete all the theory, then I'll start with the problems. I'll solve at least one or two problems on each topic, so that you can get a clear idea of what we have studied.